Look at a basic mechanical system in motion. We have a heavy mass attached to a spring and damper, oscillating up and down over time. Three distinct physical properties govern every millimeter of this movement. You have the inertia of the mass resisting acceleration, the energy dissipation of the damper slowing things down, and the restoring force of the spring constantly trying to pull the system back to center. To calculate exactly where that mass will be at any given millisecond, engineers rely on this governing differential equation. The variables m, c, and k represent our mass, damping, and stiffness, and they all react to whatever external force is driving the system, written here as f of t. When that external force is a repeating physical vibration, f of t expands into a pure sine wave, tracing the physical oscillation through time. Because the physical force pushing the system is a sine wave, human instinct dictates that the resulting physical movement of the mass will also take the shape of a sine wave. Following that logic, you would naturally take standard sine and cosine functions and plug them directly into the differential equation to find your solution. A sine wave perfectly tracks the physical reality of the motion. But using that same physical wave as the mathematical tool to solve the system is a trap. Attempting to solve forced differential equations using physical sine waves creates a grueling mathematical bottleneck. The immediate consequence is a severe alignment problem. Physical damping introduces phase delays, meaning the input force and the output motion no longer peak at the same time. To force a solution in this state, you have to rely on pages of complex trigonometric identities just to keep the equations balanced. The alternative is to stop fighting the calculus entirely. We can abandon the physical time domain and map the vibration into an abstract mathematical space instead. Mapping mechanical vibration into the complex plane is a deliberate, surgical tool. Engineers use it for one reason: to entirely bypass the need for time domain calculus. Here is exactly where sine waves break down. Watch what happens when we run the calculus. If your position is a sine wave, taking the first derivative to find velocity transforms the structure into a cosine. Taking the second derivative for acceleration flips it back to a sine wave, but now it is negative. Notice the exact point of failure. Calculating velocity turns a sine into a cosine. The base mathematical form actually mutates. We can take these physical derivatives and plug them back into our system's governing equation to see how they behave. The chaos stems directly from the middle term. The damping variable relies on the first derivative, which injects a cosine into an equation otherwise populated entirely by sines. Because the terms no longer match, this equation cannot simply be added together. It is practically unsolvable without introducing arbitrary mathematical compensations. You are suddenly forced to manage a cascading series of phase shift variables, solely to manipulate the left side of the equation until it balances with the right. This is the calculus trap. Forcing a physical function to solve a physical system traps you in a cycle of mismatched terms and form-changing derivatives. Euler's formula provides the exact mechanism we need to escape. The complex exponential encodes both the cosine and the sine forms simultaneously within a single term. Geometrically, you can think of this complex exponential as a three-dimensional phasor rotating over time. If you shine a light on it, the two-dimensional shadow it casts on the wall perfectly matches our standard physical sine wave. The operational shift happens here. Instead of using standard trigonometry, we redefine both our driving force and our assumed motion as this complex exponential. Making this assumption does not alter the physical reality of the mass, the spring, or the damper. It simply packages the underlying math into a structurally superior format. By executing this single shift, we unmoor the problem from the physical time domain, allowing us to solve for movement without ever touching a trigonometric identity. Let's run the calculus again, this time taking the first derivative of our newly assumed complex exponential motion with respect to time. Look closely at the outcome. The foundational base term remains absolutely untouched. It survived the derivative operation structurally identical. The only change that occurred was the extraction of the scalar multiplier, I omega, pulling straight to the front. Executing the second derivative simply extracts a second scalar, producing negative omega squared, while leaving that base mathematical form perfectly intact once again. Compare that to the standard sine wave from earlier, which mutated into a completely different trigonometric function the moment we applied the first derivative. The complex exponential possesses strict mathematical invariance. The operation of a time derivative is cleanly replaced by basic multiplication. Now we bring these newly derived complex terms back into our original system equation. Because the base complex term never mutated during differentiation, we now have a common factor shared across every single part of the equation. This allows us to mathematically cancel out the time-dependent term across the board, dropping it out completely. Removing that exponential time element leaves us with this simplified line. The differential equation has been successfully annihilated. What started as a calculus problem is now solved using high school-level algebra. If we isolate the parameters on the left side of our collapsed equation, we get a specific grouping known as mechanical impedance. To see exactly what the math is doing, we can map this algebraic grouping onto a two-dimensional complex plane. The x-axis represents our real numbers. It calculates the parameters that store energy, the stiffness of the spring, and the inertia of the mass. The y-axis represents our imaginary numbers. It strictly isolates the parameter responsible for dissipating energy out of the system, the damping. Drawing a single resultant line connecting these coordinates calculates both the total amplitude of the physical vibration and its precise phase shift simultaneously. The complex plane acts as a unified analytical dashboard. It elegantly separates energy storage from energy dissipation, managing amplitude and phase in a single geometric space. Physical mechanical systems do not inherently operate on imaginary numbers. The actual mass and spring exist squarely in reality. Engineers map equations onto the complex plane to create a strict operational shortcut, deliberately avoiding the limitations of physical modeling. Look at the difference in logic side by side. We are actively trading the friction of time domain calculus for the precision of frequency domain multiplication. In the world of vibration mechanics, complex numbers are an engineering choice, a tool that allows us to move past the limits of time domain calculus and solve vibration problems through simple multiplication.